Okay, so we are on question 315 in generalized linear models with examples in R, that book up there. Um, so let's, okay, so here we are. We're going back to a problem from an earlier chapter, problem 216. So if you want, you can go back and either watch that video or look it up in the book or find it on the Colab sheet for the last chapter. But in that question, we ran a regression model, and we'll look at that model here in a second. And now we're going to do some diagnostic analyses on it. So let's kind of get that rolling here. So the first thing that we need to do is to get the data loaded. So we need to install and load the GLM's data package, which contains the data set called crawl, which I am calling D. Okay. And then I'm also going to copy and paste what I used as the regression model from 2.16, okay? Now, roughly what this is it's a bunch of babies, and it is I believe it's the age at which they started to crawl and the temperature 6 months after they were born, which I assume means about the time that we expect babies to start to crawl. And the hypothesis was that that babies that are 6 months old during colder temperatures will take longer to crawl because they're going to be bundled up in all sorts of clothes, and it limits their mobility, and so it makes it harder for them to crawl, so they don't learn until later. Okay, so that's the basic idea. So I've ran this model. And so now we're set up to start answering the question. So the first thing we want to do is to perform a diagnostic analysis on that model. And then part two, which we'll answer at the same time, is to identify any influential or outlying observations. Okay, so the easiest way to do that is to begin by just using plot and then the name of the model, and that brings up these nice diagnostic plots here. And then I am additionally grabbing the hat values and the Cook's distance, and we'll talk about why here in a minute. So let's zoom in on this image here. Okay, so let's just kind of take in what's happening here. So the first thing I usually look at is the QQ residual plot. All right, the model seems to be doing a decent job of representing the data. There is this suspicious little guy here, number 5, and so we'll have to kind of keep an eye on that, but we'll just kind of keep moving here. The next one I usually like to look at is the residuals versus leverage plot, and that is very apropos to what we're doing in this question, which is trying to find influential observations and outlying observations. Okay, so now an influential, well, actually, let's start with a high leverage observation. A high leverage observation is one with a high hat value, okay? Or that's how we could detect it, right? And so that's why I'm grabbing hat values here. This is kind of representing, or I mean, it is our measurement of the leverage of an observation, okay? So here we have leverage plotted on the x-axis here. And so we can actually see observation 5 here, kind of the weirdo that's here. We see it here. It has a fairly large residual, but we notice that it doesn't have a lot of leverage, right? Its leverage is among the lowest, maybe the second lowest leverage value of everything here. So while it is, while it, seems to kind of stick out like a sore thumb in the model or in the output of the model, it is not what we would call a high leverage point. And it also may not be overly influential. Now, this is kind of a gray term here. So like, when is an observation overly influential? Well, in some sense, that's kind of a judgment call. But R conveniently kind of suggests, well, how about values or Cook's distance values of 0.5 and 1? And so Cook's distance here is represented, by these gray dotted lines here, okay? And so this weird observation does not doesn't cross these kind of arbitrary thresholds. But anyway, so there isn't a whole lot of evidence that it's overly influential, at least if we're buying into if we're buying into these thresholds here. Okay, just a little bit more about leverage. Okay, we can see that that it does not have a lot of leverage. That observation 5 doesn't have a lot of leverage, not only by this guy here. Um, you know, okay, so we could look at this guy here and we could just say, okay, well, it doesn't have a lot of leverage. Okay, we could also calculate the raw hat values for 5, right? And we see that its leverage value or its hat value is fairly low. Okay, but another way to visualize this is to look at its outcome value, or at least its fitted value, um, in the spectrum of outcome values. Okay, now leverage to me suggests thinking about the range of outcome values as something like a teeter-totter. Okay, so here's the teeter-totter, right here. It's basically the range that the outcome values sit on, and the further out you go on this teeter-totter, the more leverage you exert, right? If you push down with 1 pound of pressure on a teeter-totter right next to the middle, it's not going to have much of an impact. And if you go all the way up to the end, that same 1 pound of downward pressure is going to have a lot of effect on the movement of the teeter-totter, right? Because you have more leverage. Well, that same idea applies here. And here we see that 5 is basically right at the center, right at the fulcrum of that teeter-totter, which is indicative of it having very low leverage. So even though, again, it is a kind of a weird observation here in terms of the model, it doesn't have the ability to exert a lot of influence, right, because of its leverage point. Okay. Now, in general, so if we're looking then at the hat values and the Cook's distance, which are kind of our measurements here for both leverage, hat values, and influence, Cook's distance, we see that that the highest Cook's distance here has the lowest leverage. Okay, and so we can't really call that point there an outlier because of that. All right, but there's actually this interesting trend here where the highest leverage points, right, have the lowest Cook's distances, right? So in order to be an outlier, we need both high hat value and high Cook's distance, right? So high leverage and high influence. So anyway, there doesn't seem to be any real outliers here. Okay. Now for part 3, we're asked, suppose that there are that some of the babies here were twins. Which assumptions are violated from our linear regression, and do you think that this would have practical implications? Okay. So the assumption that is being violated here is that in this type of simple linear regression, we assume that all of the data points, i.e. the babies, are independent. Okay. So if we have twins in there, those babies are not independent anymore, right? They are, they share the same genetics and probably the same environment, or very close to being to the same environment. Okay. So those observations are not independent. So that's what's being violated here. Now, is this going to have any practical implications? Well, that's not entirely clear. If there's a lot of sets of twins relative to the sample size, that could have an effect. Now, but if those sets of twins are spread homogenously across all values of age and temperature, then probably it doesn't have an effect. So if they tend to cluster just by chance at one age value or one temperature value, that can be a problem. Now, there is an additional layer in this problem, which is that age here actually represents the average age at which many babies are crawling, or so one data point might actually represent dozens of babies, and so the average of dozens of babies is going to be less affected, by a set of dependent observations than if each baby entered the model all by itself. But anyway, I guess that's my answer to that. Okay.